Why Europa is more important than Mars? For decades, Mars has been the center of humanity's search for life beyond Earth. The red planet, the next frontier, the place where rovers roll across dusty plains, drilling into ancient rock, searching for signs that life once existed. Billions of dollars have been spent, missions have been planned, astronauts have trained, and the public has been told repeatedly that Mars is where we will find answers. This focus made sense. Mars is close, reachable. We've landed robots there successfully since the 1970s. The Viking landers, Spirit and Opportunity, Curiosity, Perseverance. Each mission has expanded our understanding. Mars has water ice. It has minerals that form in the presence of liquid water. It has ancient riverbeds, evidence of lakes, maybe even an ocean billions of years ago. Mars was once more Earth-like than it is now. Warmer, wetter, with a thicker atmosphere, conditions that could have supported life. And if life existed there, even microbial life, traces might still remain, preserved in the rock, frozen in the ice, waiting to be discovered. This logic drove exploration. Mars became the default target, the place where astrobiology, the study of life in the universe, focused its attention. But over the last 2 decades, something changed, not suddenly, gradually, as new data arrived, as scientists re-examined old assumptions, as missions to other worlds revealed possibilities no one had seriously considered before. The shift didn't make Mars less important. It simply meant Mars was no longer the only place worth looking, or even the best place. Europa, a moon of Jupiter, has become the new priority. And the reasons are scientific, not speculative, not based on hope or imagination, based on evidence. Evidence that Europa might not just have had life in the past, it might have life right now. Europa is small, about the size of Earth's moon. It orbits Jupiter at a distance of about 417,000 miles, completing one orbit every 3.5 Earth days. From Earth, it's just a point of light, visible through a telescope, one of 4 large moons discovered by Galileo in 1610. For centuries, it was just another moon. Unremarkable. Then in the 1990s, NASA's Galileo spacecraft arrived at Jupiter. It spent 8 years studying the gas giant and its moons, and what it found at Europa was unexpected. The surface is ice, smooth in some areas, cracked and ridged in others. The ice is young, very young, geologically speaking. Few impact craters, meaning the surface is being renewed. Something is resurfacing Europa, erasing craters, creating new ice. But the real discovery was beneath the ice. Data from Galileo suggested that Europa has a subsurface ocean, not a small lake, an ocean, global, covering the entire moon beneath a shell of ice estimated to be 10 to 15 miles thick. And this ocean is not frozen. It's liquid, vast, deep, possibly containing more water than all of Earth's oceans combined. This is not speculation. The evidence is strong. Galileo measured Europa's magnetic field. The field changes in a way consistent with a conductive layer beneath the surface. Salt water is conductive, ice is not. The magnetic measurements indicate liquid, salty water. Additionally, images from Galileo and later observations from the Hubble Space Telescope show plumes of water vapor erupting from Europa's surface. Geysers, venting water into space. This is direct evidence of liquid water beneath the ice. The existence of liquid water on Europa changes everything, because life as we know it requires water, not ice, not vapor. Liquid water. Water in a state where chemistry can happen, where molecules can move, where energy can be transferred. Life on Earth exists wherever liquid water exists. In deserts, in glaciers, in boiling hot springs, in the deepest ocean trenches. If there's water, there's a chance for life. But water alone is not enough. Life also requires energy and chemistry, the right elements in the right environment. Europa appears to have all 3. The energy comes from tidal heating. Europa orbits Jupiter in a slightly elliptical path. As it moves closer to Jupiter, the planet's immense gravity pulls on Europa, deforming it. As Europa moves farther away, the pull weakens. The moon relaxes, This constant flexing generates heat, friction, internal to the moon, tidal heating, the same process that makes Jupiter's moon Io the most volcanically active body in the solar system. For Europa, tidal heating keeps the subsurface ocean liquid despite surface temperatures of around -260 degrees Fahrenheit. Without this heating, the ocean would freeze solid. But the energy from tidal forces, combined with possible radioactive decay in Europa's rocky core, maintains liquid water. And where there's liquid water and energy, there's potential for life. The chemistry comes from the ocean's likely contact with Europa's rocky seafloor. Europa is not just ice, it has a rocky interior, a silicate mantle surrounding a metallic core. The ocean sits between the ice shell above and the rocky layer below. This is significant because on Earth, some of the most life-rich environments are places where water meets rock. Hydrothermal vents, cracks in the ocean floor where heated, mineral-rich water rises from below. These vents support entire ecosystems: bacteria, tube worms, shrimp, crabs. Life that doesn't depend on sunlight. Life that gets its energy from chemistry, from the minerals and heat coming out of the vents. If Europa's ocean is in contact with its rocky mantle, similar processes could occur. Water interacting with rock, heat from tidal forces driving chemical reactions, minerals dissolving, creating an environment where life might emerge. Not photosynthetic life, not life depending on the sun, but chemosynthetic life, life that derives energy from chemical reactions. This is why Europa matters more than Mars. Mars represents a past environment, a place that was once habitable, but is now cold, dry, and hostile. The atmosphere is thin, mostly carbon dioxide, surface pressure less than 1% of Earth's. Water exists, but as ice or trace vapor. Liquid water cannot remain on the surface. It would freeze or evaporate almost immediately. Mars lost its magnetic field billions of years ago. Without that protection, solar winds stripped away much of its atmosphere. Rivers dried up, lakes evaporated. The planet became a desert. If life existed on Mars, it likely existed billions of years ago. And if it still exists, it would be deep underground, in pockets of liquid water, protected from radiation, isolated, dormant. Europa, by contrast, represents a present environment, an ocean that exists now, energy flowing through it now, chemistry happening now. If life exists on Europa, it could be thriving, active, not a fossil, not a trace, but living organisms, in an ocean, right now. This distinction has reshaped scientific priorities. NASA's focus has shifted, not entirely away from Mars. Mars missions continue. Perseverance is collecting samples for eventual return to Earth. Future missions will analyze Martian soil and ice in greater detail. Mars remains important, but it is no longer the primary target for the search for life. Europa has taken that position, and NASA has committed resources to match. The Europa Clipper mission, scheduled to launch in October 2024, represents one of the largest and most ambitious planetary science missions ever attempted. The spacecraft will not land on Europa. It will orbit Jupiter and conduct dozens of close flybys of the moon, passing as low as 16 miles above the surface. The mission's goals are specific: not to find life, to assess habitability, to determine whether Europa's ocean has the conditions necessary for life, to measure the thickness of the ice shell, to analyze the composition of surface material, to detect and study any plumes of water vapor, to map the magnetic field in greater detail, to confirm the ocean's existence, to understand its chemistry. Europa Clipper carries 9 scientific instruments: cameras, spectrometers, magnetometers, ice-penetrating radar, a thermal instrument to detect areas of warmth, a dust analyzer to study particles ejected from Europa's surface. Each instrument designed to answer specific questions about Europa's habitability. The mission will not search for life directly. That would require landing, drilling through miles of ice, sending a probe into the ocean. Technology for that doesn't exist yet. Europa Clipper is a reconnaissance mission, a survey, gathering the data needed to plan future missions. Missions that might one day reach the ocean. The challenges are significant. Jupiter's radiation environment is extreme. The planet's magnetic field traps charged particles, electrons and ions. These particles bombard Europa's surface constantly. Radiation levels around Europa are intense enough to damage electronics, to degrade materials, to make human exploration, at least on the surface, extremely difficult. Europa Clipper is designed to survive this. The spacecraft's electronics are housed in a thick-walled vault, shielded, protected. The mission profile minimizes time spent in the radiation belts. The spacecraft will orbit Jupiter, not Europa, conducting flybys, dipping into the radiation, collecting data, then retreating to safer distances. Another challenge is the ice. If future missions attempt to reach the ocean, they will need to penetrate 10 to 15 miles of ice. On Earth, the deepest ice drill has reached about 2 miles. Drilling through Europa's ice would require technology far beyond current capabilities. It would require power, heat, drilling equipment that can operate autonomously in extreme cold for years or decades. And there's the cold itself. Surface temperatures on Europa hover around -260 degrees Fahrenheit. Materials behave differently at those temperatures. Metals become brittle, lubricants freeze, batteries lose efficiency. Any surface mission would need to account for this: heat sources, insulation, redundancy. But these challenges are not reasons to avoid Europa. They are reasons to confront it carefully, methodically, with the understanding that the potential reward justifies the difficulty. Because if Europa harbors life, even simple microbial life, the implications are profound. Life on Earth exists in extraordinary diversity, but all of it shares a common origin, a single tree of life, DNA or Na, cells. We are all related, descendants of the same ancient ancestor. If we find life on Europa, and if that life is independent, not related to Earth life, it would mean life arose twice in the same solar system, independently. That would suggest life is not rare, not a cosmic accident, but common, perhaps inevitable wherever the right conditions exist. It would mean the universe is full of life, not just on planets, but on moons, in subsurface oceans, in places we haven't even considered yet. This is why Europa is more important than Mars. Mars can tell us about the past. Europa can tell us about the present and possibly the future. Mars can tell us whether life arose in multiple places within our solar system. Europa can tell us whether it survived, whether it persists, whether the universe is alive in ways we've only begun to imagine. Europa is not alone in this regard. Other moons have subsurface oceans. Enceladus, a moon of Saturn, has geysers venting water into space. Titan, also orbiting Saturn, has liquid methane lakes on its surface and possibly a subsurface water ocean. Ganymede, another moon of Jupiter, likely has an ocean as well. The outer solar system may be full of ocean worlds, but Europa is the closest, the most accessible, the one we understand best. It is the logical first target, the place to test our methods, to develop the technology, to learn whether subsurface oceans can support life. The search will take time. Europa Clipper will arrive at Jupiter in 2030. It will spend years conducting flybys, collecting data, transmitting findings back to Earth. Scientists will analyze that data, refine models, plan the next steps, a lander mission, a drilling mission. Someday, perhaps, a probe sent into the ocean itself. We will not have answers quickly. Astrobiology operates on timescales of decades. Missions take years to plan, years to build, years to reach their destinations. And the answers, when they come, may be ambiguous, inconclusive, requiring more missions, more data. But this is how science works, slowly, carefully, building knowledge piece by piece. Europa represents the next piece, the next step in understanding whether we are alone. Mars will always matter. It is the planet we will likely visit first with humans, the place where we might build habitats, conduct research, test technologies for deep space exploration. Mars is important for human spaceflight, for expanding our presence beyond Earth. But for the question of life, Europa has become the priority, because it is not a dead world with ancient history. It is an active world with a present environment. An ocean, energy, chemistry, the ingredients for life, right now, beneath the ice. We do not know if life exists there. We may never know without going. But the possibility is real, grounded in evidence, supported by data. And that makes Europa worth the effort, worth the cost, worth the decades of patient work ahead. Because if Europa has life, it changes everything. Our understanding of biology, our place in the universe, the likelihood of life elsewhere. And if Europa doesn't have life, that answer is valuable too. It tells us something about the conditions required, about the boundaries of habitability, about where to look next. Europa is more important than Mars, not because Mars doesn't matter, but because Europa represents the question we need to answer most, not whether life existed, but whether it exists now, in places we didn't expect, in ways we are only beginning to understand. The spacecraft is being built, the instruments are being tested, the mission is scheduled, and in a few years we will begin to find out. Not whether Europa has life, but whether it could, whether its ocean is habitable, whether the conditions are right. And if they are, we will keep going, deeper, closer, until we know, or until the ice keeps its secrets.